In the entire 300,000-year history of the human species, no machine has ever been built that can do what this one does. Not the Saturn V that carried astronauts to the moon, not the space shuttle, not the most powerful nuclear reactor, the largest cargo ship, or the heaviest aircraft ever flown. What SpaceX just completed testing at Starbase, Texas, is something genuinely unprecedented in the history of engineering. A fully reusable two-stage rocket that produces 16 million pounds of thrust at liftoff, can carry 200 metric tons to orbit, and is designed to fly again and again like a commercial aircraft between launches. And its first flight is coming in weeks. This is Starship version 3. And if you want to understand why this machine is not just the most powerful rocket ever built, but arguably the most consequential piece of engineering in human history, then stay with me. Because the story of what SpaceX has actually built here goes far deeper than the headlines. Let's start with raw power, because the numbers demand to be stated clearly before anything else. Starship version 3 is powered by 33 Raptor 3 engines on its super heavy booster stage, plus 6 Raptor 3 engines on the Starship upper stage. 39 engines total across the full vehicle. Each Raptor 3 engine delivers approximately 280 metric tons of thrust, operating at a chamber pressure of around 350 bars, the highest operating pressure of any rocket engine ever produced at scale. When all 33 booster engines ignite at liftoff, the combined thrust output is approximately 16 million pounds of force. To put that number in human terms, 16 million pounds of thrust is roughly double the thrust of NASA's Saturn V rocket, which for 55 years held the title of the most powerful rocket ever flown. It is nearly twice the thrust of NASA's current Space Launch System, which produces 8.8 million pounds at liftoff. Starship version 3 doesn't just beat the competition, it makes everything that came before it look like a model rocket. But raw thrust is only part of the story. What makes Starship V3 truly revolutionary is what it can do with that thrust. The Saturn V, for all its extraordinary power, was expendable. Every single Saturn V rocket that ever flew was destroyed in the process of flying it. Each one cost the equivalent of billions of dollars in today's money, and it was used exactly once. The space shuttle was partially reusable. The main engines and the orbiter were recovered, but the external tank was discarded on every flight. NASA's current SLS rocket is fully expendable. Every launch consumes the entire vehicle at a cost estimated between $2 and $4 billion per flight, depending on the configuration. Starship version 3 is designed to be fully and rapidly reusable. Both stages, the Super Heavy booster and the Starship upper stage, are designed to return to the launch site, be caught by the mechanical arms of the launch tower, and fly again within days or weeks without major refurbishment. This is not a theoretical design goal. SpaceX has already demonstrated both stage recovery in practice. On October 13, 2025, during Flight 11, the final test flight of the version 2 hardware, both the Super Heavy booster and the Starship upper stage successfully completed the mission objectives. The booster returned to Starbase and was caught by the mechanical arm system nicknamed Mechazilla. The upper stage performed its own controlled re-entry and landing in the Indian Ocean. For the first time in the history of the Starship program, both stages came home. That demonstration of full vehicle recovery set the foundation for what version 3 is now inheriting, a validated architecture for full reusability, now applied to a rocket that is substantially more powerful and capable than the vehicle that proved the concept. The Raptor 3 engine is the heart of what makes version 3 different. Pace ex-VP of Starship Engineering, Bill Riley, and Director of Starship Engineering Charlie Cox both appeared in SpaceX's April 24, 2026 documentary, a 25-minute engineering briefing titled Test Like You Fly, to formally introduce version 3 and walk through the Raptor 3 in specific detail. The core design philosophy of Raptor 3 represents a fundamental shift from the approach of every previous rocket engine program in history. Normally, when engineers want a more powerful engine, they accept that it will be heavier, more complex, and more expensive to manufacture. Raptor 3 breaks that rule. It delivers almost double the thrust of the original Raptor 1 engine, while costing 4 times less to manufacture and being significantly lighter. Each Raptor 3 saves 2,125 pounds of weight compared to an equivalent previous generation engine. Across 33 booster engines, that weight reduction totals approximately 42.9 metric tons. 42.9 metric tons of saved mass that can instead be used as payload, as propellant, or as structural margin. More power, less cost, less weight, all at the same time. That combination is not just impressive engineering, it is a fundamental rethinking of what rocket engine design can be. The external appearance of Raptor 3 tells part of the story immediately. The original Raptor engine had extensive external plumbing, gas generators, heat shields, complex pipe routing that wrapped around the outside of the engine. Raptor 3 eliminated the external gas generator entirely, The external plumbing was dramatically simplified. The heat shield that protected components on previous versions was removed because the redesigned engine structure no longer requires it. The engine that emerges from this simplification is visibly cleaner. Fewer parts means fewer potential failure points, fewer inspection requirements, fewer parts to replace between flights, and a faster turnaround time between uses. SpaceX's stated objective for Raptor 3 is aircraft-like reusability, not just surviving multiple flights, but doing so without significant refurbishment between them, the same way a commercial jet engine flies thousands of hours between major maintenance events. No rocket engine program in history has ever achieved this standard. Raptor 3 is designed to be the first. The structural changes to version 3 extend far beyond the engines. Both the Super Heavy booster and the Starship upper stage have been stretched and enlarged for version 3. The Starship upper stage has been extended by approximately 2 to 3 meters, with the additional length used to accommodate larger propellant tanks. The Super Heavy booster, designated Booster 19 for Flight 12, has a lengthened propellant section with a revised forward dome and relocated grid fin attachment points. The grid fin system itself has been completely redesigned. Version 2 used 4 grid fins, the large aerodynamic control surfaces that steer the booster during its return to the launch site and slow it before the catch. Version 3 uses only 3 grid fins. But these 3 fins are 50% larger and substantially more robust than their predecessors, providing more steering authority and more aerodynamic braking capability per fin, while reducing the total system weight and simplifying the hydraulic system that deploys them. The full version 3 stack, Booster 19 and Ship 39 stacked together, stands approximately 408 feet tall. That is 9 feet taller than the Statue of Liberty from base to torch. It is taller than a 40-story building. When fully fueled with liquid methane and liquid oxygen, the total mass of the vehicle approaches 5,300 metric tons, 11.7 million pounds. That is the mass of approximately 80 fully loaded 747 aircraft. All of that mass is sitting on a single launch mount at Starbase, waiting to be thrown toward orbit by 16 million pounds of thrust. Now, here is the number that matters most for understanding why this machine changes everything. Starship version 3 in reusable configuration, meaning both stages fly back and are recovered, is targeted to deliver more than 100 metric tons to low Earth orbit per flight. In fully expendable configuration, where the hardware is expended rather than recovered, that payload capacity climbs toward 200 metric tons. The current record holder for payload capacity to low Earth orbit in a non-reusable configuration is the Saturn V at approximately 140 metric tons. Starship V3 in expendable mode exceeds the Saturn V's. Starship V3 in reusable mode delivers more payload than any current operational rocket on Earth, by a wide margin. The nearest competitor in the reusable category is SpaceX's own Falcon Heavy in its expendable configuration at 64 metric tons, and V3 more than doubles that. But payload capacity numbers in isolation don't tell the full story of why version 3 matters. The reason it matters is what happens when you combine 100 plus metric tons of reusable payload capacity with a launch vehicle that can turn around within days or weeks and fly again. The economics of space launch are transformed completely. Every industry analyst who has modeled the cost implications of fully operational Starship V3 reaches the same conclusion. The cost per kilogram to low Earth orbit drops from thousands of dollars, where it has sat since the beginning of the space age, to potentially tens or hundreds of dollars. Not a 20% improvement, not a 50% improvement. A reduction of 1 to 2 orders of magnitude. The entire economic structure of what is possible in space changes when that happens. SpaceX's own Starlink program illustrates the point concretely. Version 3, Starship, is large enough to efficiently carry the full-sized next-generation Starlink satellites, which are larger and more capable than the versions launched on Falcon 9. The internal payload deployment mechanism of version 3 has been significantly enlarged, allowing far more satellites per flight than any previous vehicle. SpaceX aims to compress the deployment timeline for new Starlink constellation generations, dramatically using V3 flight cadence, potentially launching hundreds of satellites in a single mission where multiple Falcon 9 flights would previously have been required. For NASA's Artemis program, the stakes could not be higher. NASA has committed $4 billion to a modified version of Starship, the Starship Human Landing System, or HLS, to return astronauts to the moon's surface for the first time since 1972. The planned landing mission, Artemis IV, currently targets 2028, but here's the complexity that most coverage skips over. Getting Starship HLS to the moon and back requires orbital refueling. The vehicle cannot carry enough propellant from Earth to make the full round trip to the lunar surface and back. SpaceX must launch multiple tanker variants of Starship into orbit before the crewed landing, each carrying liquid methane and liquid oxygen, to fuel up the HLS vehicle before it departs for the Moon. Current estimates suggest that a single lunar landing mission may require between 10 and 40 tanker flights, depending on propellant boil-off rates and transfer efficiency. Version 3 includes new external docking adapters and internal plumbing designed specifically for this in-orbit propellant transfer architecture, what SpaceX engineers describe as a gas station in the sky. Whether that system can be demonstrated reliably enough and at sufficient scale to support the Artemis mission timeline is the central technical challenge that stands between version 3 and the Moon. On April 24, 2026, just 4 days ago, SpaceX released the Cosmos Test Like You Fly documentary that offered the most detailed public engineering briefing on Starship in the program's history. The video is not a highlight reel. It is a structured engineering document that walks through the lessons learned from Flights 1 through 5, the philosophy behind version 3's clean sheet redesign, and the specific changes made to both the booster and the ship. SpaceX VP Bill Riley and Director Charlie Cox appear on camera to explain their decisions. The manufacturing footage in the video makes clear that SpaceX is no longer treating Starship as a prototype program. Production infrastructure is being built in parallel with flight testing. The factory layout visible in the documentary shows version 3 hardware being built on a production line, not assembled one-off in a workshop. The company that once built rockets to fly and learn is now building rockets to fly, land, and fly again, at commercial scale. The cryo-proof testing sequence shown in the documentary provides specific structural validation data at a level of detail SpaceX rarely shares publicly. Liquid propellant at approximately 80 Kelvin, roughly negative 193 degrees Celsius, is used to pressure test tank structures at 70% proof pressure. This cold temperature structural testing is essential because the vehicle's stainless steel tanks must withstand both the cryogenic temperatures of the propellant and the extreme aerodynamic and thermal loads of flight and re-entry. The footage confirms that both Ship 39 and Booster 19 have passed their cryo-proof milestones. The full 33-engine static fire of Booster 19 conducted on April 16th confirmed the propulsion system's readiness. The 6-engine static fire of Ship 39 on April 15th confirmed the upper stage. Both stages are cleared for flight. Flight 12, the first integrated flight test of version 3, is targeting early to mid-May 2026. It will be the 12th overall test flight of the Starship program, the first ever flown by a version 3 vehicle, and the first opportunity to validate the full V3 performance envelope in real flight conditions. SpaceX will almost certainly attempt to push beyond what Flight 11 demonstrated, expanding the flight profile, testing new systems, gathering data on the V3 structural and propulsion performance under actual flight loads. There are also long-term commercial implications that extend far beyond NASA. SpaceX recently filed confidential IPO paperwork with the Securities and Exchange Commission in what analysts are describing as the potential largest initial public offering in stock market history. The company's valuation, driven in significant part by the Starlink constellation and the Starship vehicle's future revenue potential, is estimated in the hundreds of billions of dollars. The context that all of this sits within is worth stating plainly. Human beings have been dreaming about becoming a multiplanetary species since before there were rockets capable of reaching orbit. For most of that history, the dream has been economically impossible. The cost of launching mass to orbit has been so high that even the most ambitious government programs could only send a handful of people at a time for missions measured in days or weeks. Starship version 3, if it performs as designed and achieves the launch cadence SpaceX is targeting, changes that equation at the most fundamental level. A vehicle that can carry 100 metric tons to orbit for a fraction of today's launch costs, flying potentially dozens of times per year from a single pad, reusing both stages, turns the dream of large-scale human presence in space from an economic fantasy into a logistics problem. A hard logistics problem, but a solvable one. The Saturn V gave humanity its first glimpse of what was possible beyond Earth. For 55 years, nothing surpassed it. Now, in a field in South Texas, 2 stages of polished stainless steel stand 408 feet tall, waiting for the countdown. The giant is awake, and the universe is closer than it has ever been.